Hello, welcome on our next lecture on deep learning. In the last lecture, we've talked about gradient descent. Now in deep learning, we often apply a variation of gradient descent, which is called stochastic gradient descent, where the gradient is not computed exactly, but a stochastic, so a randomized version of this gradient is computed by sampling individual data points from your data set instead of evaluating your loss function on the whole data set. So let's look at how this works. In machine learning problems, our objective function is typically the average over the losses over all the individual training data points. So if, for example, a regression loss, which is the squared error, so you will have a prediction value for your regression problem and the real value. You're predicting the house price and you have the real house price. You're looking at the difference, you're squaring it. So it's a squared error. You have that for all your n training data points and your mean squared error. Then the average over all these losses, these individual squared differences between predicted house price and real house prices. So you have average over loss functions, little l, over all our n training examples. And each of those coordinates of f is the loss of such one example. So f of x is 1 divided by n times the sum over all these fi's. And similarly, if you compute the gradient then actually becomes the average over the gradients of these individual fi's. So all of these fi's take the same parameter vector x, but they all yield the individual losses for this one training example and the individual gradients, and the complete gradient is then the average over all of these gradients. Now the cost of computing all of these gradients is, well, the n of them, so the loss of computing this gradient, which is the average over n of them, is O of n per iteration. Now stochastic gradient descent reduces the cost at each of operation by uniformly sampling a single data point I and computing the gradient and the objective function only for this one data point. So you're only looking at one of those n losses. And then you're computing the average over this one. Yeah? So your update in this case for stochastic gradient descent becomes x minus eta, the learning rate, not the gradient of the whole function, but the gradient of this one ith component function. Of course, because we only have to look at one example and not on n, we're reducing the cost of computing this gradient from O of n to O of 1. Thus, computation is much faster, going from linear to constant. However, it's only an approximation, so how well does this work? Well, actually, it turns out that if we compute the expected value over these component-wise gradients, we actually get the real gradient back. So the expected value over all our n training examples, so it's an empirical expectation over our data set, is equal to the average. So it's 1 divided by n, the gradient of the ith component function, which is exactly our real gradient. So in expectation, stochastic gradient descent yields the right gradient, just that each example is different, but if you average over many of these, you get the correct gradient back. How well does this work in practice? Well, if we look at this function here, then we start here with stochastic gradient descent, we see that actually it works quite well. We do see that in contrast to gradient descent, which would walk somewhere like this, it actually has some wiggliness to it. But each individual step is much cheaper to compute because it's only O of n. Thus we can afford to do more steps. This usually results in a speed up compared to gradient descent whenever our real function is just the sum over all these component functions, such as in machine learning, where we have our individual losses of all our training data sets, and we're computing the average or the sum over all of these losses. Now, stochastic gradient descent we could also do for logistic regression. Also in logistic regression, your loss is the sum over all your training data sets. Thus, we could evaluate the gradient of these components. So we would always compute the gradient of the regularizer exactly, and then randomly sample one of our training data points and then compute the stochastic gradient with respect to that one data point. So it would be applicable. The larger our data set is, so the larger n, the more expensive it is to use the batch gradient descent, so computing the whole gradient. Because it's a batch computation over all the n data points, we call it also sometimes batch gradient descent, in contrast to stochastic gradient descent, which only looks at a single data point. So the larger our training data, the larger typically the speed benefit of stochastic gradient descent. So stochastic gradient descent looks at a single data point at a time. Batch gradient descent looks at all n data points. Of course, you can also do something in the middle, and that's a so-called mini-batch stochastic gradient descent. In mini-batch gradient descent, you're uniformly sampling a random subset, so-called mini-batch, of fixed size from your whole training data set, and instead of averaging over the whole data set as in batch gradient descent, you're now averaging only over this mini batch. So you're summing your gradient of all these component functions of the mini batch, and you're dividing by the size of the mini batch. Now in each time step little t, we use random sampling to get a different mini batch. And then we compute our update. Xt is set to the previous, xt minus 1 minus our mini batch gradient gt times, again, a small learning rate eta t. Now, of course, if we're sampling the mini batch, now we have to think about the sampling scale. We said before that we're sampling uniformly. Now, of course, you can sample either with replacement or without replacement. Now, if you're sampling with replacement, then you allow for duplicate examples either in the same mini batch or in two mini batches after each other. And this comes at this downside that you actually may sample the same data point multiple times. However, it comes with the upside that it gives you an unbiased estimate of the gradient. Now, if you sample without replacement, it has the benefit that you're guaranteed to see more of the n samples. However, for data sets that are small in size, it has a sequential bias. So say you've already sampled xj as your first element of the mini batch. Now the probabilities for sampling the others are now modified. Still, this is only an issue for very small data sets where mini batch gradient descent is usually not applied because you can just compute the whole gradient, and in practice it's most commonly used. A limitation of stochastic gradient descent that we so far have not discussed is that it doesn't converge. Why doesn't it converge? Well, in gradient descent, if you are at the optimum, your gradient vanishes, it goes to 0. However, if it's a stochastic gradient, your expected gradient may be 0. However, each stochastic realization of it, because you're only subsampling parts of the data, is actually non-zero. So if we would just, with a fixed learning rate, let stochastic gradient descent run, or mini batch stochastic gradient descent similarly, actually this gradient has sort of a constant variance, and thus it would in a range around the optimum just meander around, uniformly around this optimum. In practice, we address this by reducing the learning rate from iteration to iteration. So we're applying a decay. For example, we would set the learning rate eta at iteration t to eta times the time step to the power of alpha, where alpha is a negative number. Alternatively, we can also set it to some fixed eta times alpha to the power of t, alpha to some positive number that is a little bit smaller than 1, such that it's actually decreasing over time. So we're reducing the learning rate every iteration or every several iterations. You could also think about t being actually not every iteration, but several iterations. And because we're now multiplying in each update the gradient with eta t, and eta t is decreasing in magnitude over time, thus the variance of the whole learning rate and of this gradient times this learning rate decreases over time. The cost in mini-batch stochastic gradient descent in each iteration is, well, it's not O of n for batch gradient descent, it's not O of 1 for stochastic gradient descent, it's O of the size of our mini-batch. Now the runtime depends very much on the mini-batch size. In practice, it's also important to maximize the efficiency of the data transfer and of your RAM, because you want to be able to compute as many as these operations as possible in parallel. So if you're choosing a small batch size and you have a GPU which actually has many cores, then you can think of actually doing all of these operations at the same time for a small batch, and thus going back to something that is O of 1 in terms of wall clock time. However, you need to make sure that the data gets there in time. So register size, RAM usage, data transfer is important in order to set the right batch sizes. So relatively small batch sizes make better use of parallel processing, and larger batch sizes are closer to the batch gradient descent, also the gradient descent that uses the whole data set. However, usually you only need a small subset to get a good gradient direction that is already quite sufficient to get this direction. So there's a lot of redundant information actually in your n data points. So these extra computes to go to a larger batch size may actually not help you to get a much better gradient. So there is this trade-off of getting a right mini batch size. But the fact that there is a lot of redundant information, we often actually would like to go through the data set in total more often if we use larger batch sizes. Thus, for larger batch sizes, we typically need to increase the number of training epochs. So one epoch is typically defined as the number of iterations that you need in order to go through your whole data set once. So in batch gradient descent, this would be a single iteration. In stochastic gradient descent, this would be after n iterations, and in batch gradient descent, something like n divided by the size of your batch. And well, if you do larger batch sizes, you do fewer iteration per epoch, and because larger batches have this little bit redundant information, you might need to do more epochs. So let's look at some runtime comparisons between stochastic gradient descent for different batch sizes. Here we see sort of the number of epochs that are needed with a batch size of 1,500. And here's the number of epochs needed for a batch size of 10. And you see that in order to arrive at a similar loss, you need many more epochs for larger batch sizes than if you work with a smaller batch size. Similarly, if we look at runtime, And we see that a too small batch size, namely batch size of 1 as in stochastic gradient descent, can take longer than the full batch gradient descent. However, if we pick a batch size, mini batch size of the right size, we can be faster than batch gradient descent. And now for larger data sets, this discrepancy would even increase. So let's summarize. Mini batch stochastic gradient descent uses random uniform sampling to get a small mini batch of training examples and computes a stochastic gradient estimate from only this mini batch. And now in practice, the learning rates for a mini batch stochastic gradient descent needs to decrease using some scheduling. The time requirement for mini batch stochastic gradient descent is typically somewhere between the time that is required for stochastic gradient descent and the complete gradient descent, so batch gradient descent, on a single epoch. So with this, I would like to say thank you and goodbye and see you next time. Bye-bye.